Hello my friends, in this video we're going to learn how astronomers calculate positions of planets more accurately than can be done with only Kepler's laws of motion. And the way they get the positions of the planets more accurate is by analyzing what are called perturbations. And once we understand perturbations, we can then go on and understand exactly what the mean node and true node are, and whether either of them is a real node, and we will see that the true node is the real node of the moon. Now, in terms of the nodes, let's start connecting what we're learning here to the way we describe planetary positions. A better term for the mean position of a planet or point. So when we talk about the mean node, or the mean sun, or something like that, a better term is unperturbed position. It is the position determined by Kepler's 3 laws and stopping right there. So if you apply Kepler's 3 laws that we learned about in the other 3 videos, and you apply that to the 6 orbital elements, you will come up with a position of the planet where the planet moves very smoothly, like Mars would move very smoothly, Jupiter, Saturn, Earth, all the planets, Moon around the Earth, they're all moving very in a smooth, gradually increasing speed as they get close to the sun, slowing down as the planets get farther from the sun. In this smooth way is what you obtain from Kepler's laws. That is the mean position. The reason I'm not fond of the term mean position, because mean means average. And to me it implies, and not just to me, because I've heard astrologers say this and get confused about it and wondering what's going on. And they'll ask questions like, is the mean position of the node mean over what time period? Well, the mean position is not calculated from observations. It's not where you take the position of, say, the nodes at 2 points in time. It's simply Kepler's laws of motion without any perturbations, and we'll learn what perturbations are. So anyway, bottom line is this: a better term to use than mean position is unperturbed position, meaning the position of the planets after you apply Kepler's laws and before you take into account perturbations. Okay. The unperturbed moon's node is a better term because the mean node is not calculated by obtaining an average position over great periods of time, as I just explained. It is calculated by applying Kepler's laws of planetary motion using the orbital elements for the moon. And it is based on observations of the size and direction of the moon's orbit and how it changes gradually over time. The word mean, as in mean values, are the orbital elements that are not adjusted for the effect of perturbations. Okay, that's just saying what I just said. Now you could calculate a mean moon, a mean Mercury. We have a mean node. We can also have a mean moon. The mean moon would be the moon that corresponds to the mean node. Mean means unperturbed. Let's remove the word mean and substitute unperturbed. You have an unperturbed node. That's the basic orbital element that was observed. And from that unperturbed position, using Kepler's laws, you obtain the position of the planet. That's the unperturbed planet. In astrology, we're never interested in the unperturbed position of the moon, Mercury, Venus. Nobody has ever asked us, our software companies, can you give me the unperturbed position of Mercury or Venus? Like not where it really is, but where it would be applying just Kepler's laws. And why would you want that? It's not where it is. In the same way, why are we interested in the unperturbed moon's node? It's not where it really is. So, I have here at the bottom, it is strange and arguably bizarre that we use the unperturbed moon's node, but not the unperturbed moon, because the unperturbed node is what determines the position of the unperturbed moon. They go together. You use the basic node position that's observed using Kepler, and then apply Kepler's laws. Anyway, in astrology, we never use unperturbed positions. All I'm saying is that. We never use unperturbed positions, except for some reason with the moon's node. It seems to me like an odd exception to the rule. The only case where we're using an unperturbed position. Now, let's get a visual example of this. Let's look at the moon's mean node and true node and a graphic ephemeris for 20 years. Let's look at it. I've got a graphic ephemeris here. This line is the mean node position of the moon from 2006 to 2024. It's a straight line. This is a 360-degree graphic ephemeris. Maybe I should pull this in a little bit so you can see the whole thing. I've got it going off the area we're capturing so you can see that a little bit better. Let me bring this down. But anyway, just to show you what I'm saying, okay, let me drag this up here. Okay, now you can see this a little bit better. Let me drag the right side over. But on the left side, you now see it says 0, 30, 60, 90, 360. This is a 360-degree ephemeris. And you see the glyphs Aries through Pisces. So it's a 360-degree ephemeris. That's the position of the node. In 2006, the node retrograded into Pisces, and it takes about 18 and a half years to go through the zodiac. Now, watch this. I'm going to go to preferences, and then common means preferences not just for the graphic ephemeris, but throughout these Kepler workshop features, and I'm going to check true node, true moon's node. It was not checked, means we were using the mean node. Click OK. Now I've changed the setting. I'm going to right click and click OK to recalculate this ephemeris. There's the true node. That is the movement of the true node. Why is it wavy? Because the speed is changing. That's the true node. If we use the mean node, that is using only Kepler's laws of motion. It's kind of fascinating to watch this. Let me do it one more time. I'm going to go to Preferences, Common. I'm going to uncheck True Moon Node. So we're going to use the Mean Node. Now watch this. When I click OK, I'm going to slide this to the right so you can see it. As soon as I click OK, watch this line straighten out. I click OK. See that? It just straightened out. Now that straightening out, this is now the mean node. Is that because an average position of all those true nodes were taken? No, it's actually just the opposite. Before you can get the true node position, you must first calculate the mean node position. Make sense? Remember, the better word for mean node is unperturbed. See, these words confuse us. If I say it this way, before you can get the actual position of the node, we must first calculate its unperturbed position. That should make more sense. Or if I said, before we can calculate the position of Mercury, we must first calculate its unperturbed position. Is that true or false? Let me ask the question again. Before we can calculate the actual position of Mercury, do we have to first calculate, or do astronomers, not we astrologers, but astronomers working from, you might say, the ground up? Would an astronomer calculating from scratch, would the astronomer have to first calculate the mean position, not the mean, the unperturbed position of Mercury before calculating its actual position? Yes or no? Answer yes. First, we apply Kepler's laws. Kepler's laws give us a fictitious, perfect planet that gradually speeds up as it gets closer to the sun and then slows down and has this nice smooth motion. Now we're going to learn about perturbations. Perturbations disturb the smooth motion. And they disturb the smooth motion of anything, whether it's the node or the moon or Mercury. They disturb its smooth motion. Okay, let's learn more about perturbations. So anyway, before we go to that, I just wanted to show you that the mean node does in fact, this demonstrates, that's the mean node moving at that very smooth, same speed. Why? Is it really a mean node? No, it's not mean, it's unperturbed. It's the position determined from Kepler's laws. Kepler's laws accurately predict where anything is, except they're a little bit inaccurate due to these perturbations. Okay, let's learn about the perturbations. Okay. Excuse me. Okay, I've already talked about this. We're going to see that in learning about perturbations, we're going to learn that the true node really is a true node. Let me read this whole slide. There is a popular idea among astrologers, including astrologers who understand the astronomical foundations of astrology. People who really understand the astronomy often say that the true node may not be where the actual node is. What they're saying is that the true node is not necessarily the actual node. It's a thing, but not the actual node. Well, over the past few years, I've done some new calculations and original calculations that show that the true node is where the actual node is. That was not obvious until we did the additional analysis. Now it's clear, at least to me, and I'll explain my logic, that the true node is where the node actually is. Just like when you look at the position of Mercury, Venus, or Mars in an ephemeris, that's where they actually are. And the true node is where the moon's node is. I'll take you through this whole thing and you will then be able to understand all this. Okay. All right, so I've already explained this, but just to repeat, we understand that the unperturbed position of the planet is calculated by using Kepler's laws of motion with the 6 orbital elements. The unperturbed position of a planet is calculated first. I just emphasize that. You must calculate that first. That's the way the formulas work. And then the perturbations are applied to improve the accuracy. So you always have an unperturbed position first. The mean node is the unperturbed node, and then the perturbations are applied to it to find out its actual position. Okay, now this is what perturbations are. The idea is very simple. Perturbations are just gravity. It's just gravity. When things are close to each other, there's a gravitational attraction. Excuse me. You know from watching movies and reading about outer space exploration that when astronauts go up in space and they get very far away from the Earth, eventually there's no gravity at all. Gravity gets weaker and weaker and weaker until there's no gravity. So the closer you are to the surface of the Earth, the more you're pulled by the Earth. We all know that. So as two objects get farther away from each other, the gravitational attraction between them decreases. And the larger object will more obviously pull on the smaller object. Actually, gravitation is mutual. We are pulling the Earth towards us, as well as the Earth pulling you to it. It's just that we're so much smaller than the Earth, it's negligible. It's just, it's like you can just ignore it. But two objects attract each other as they get close to each other. So here's what happens with planets going around the sun. In this image on the right, we've got Mercury towards the bottom, slightly right of bottom. Venus is to the left. What happens if Mercury had traveled around to where this X is, and Venus was still here? What if Mercury and Venus were lined up, in other words? And of course that happens. from the Earth's point of view, when the sun is opposition let's see, the sun, the Earth, Mercury, Venus, Earth would be here. So from the Earth's point of view, when Mercury is conjunct Venus and conjunct the sun, suppose all three were conjunct. Suppose the Earth was right here. These three are conjunct. Then Venus and Mercury are close enough to have a gravitational attraction, an increased gravitational attraction, and that's going to disturb their orbits. When it's this simple, when two planets get close to each other, they disturb their orbits. They distort them because they're pulling on each other. They're like magnets. Everything is a magnet to everything else. I shouldn't say magnet because magnetism technically is something different from gravity. But gravity and magnetism have a broad kind of similarity in that there can be an attraction. I mean, just in common sense terms, that there's an attraction when two things get close to each other. That's a perturbation. They could have been called distortions or disturbances. The word that came up and that got used was perturbation. You can imagine the number of different words. People could have called it gravitational something or other. It got to be called perturbations. Perturbation just means planets get close to each other and they attract each other and they will slow each other down or pull each other closer to each other. They're going to change that nice smooth motion of the planet. So perturbations are complicated. You have to determine how close the planets are to each other, and you need to know something else. You need to know how heavy they are. We call it mass, but you can think of mass as similar to weight. We call it mass because the weight of an object depends on how close it is, like how close you are to Earth determines your weight, but the mass is the same. Anyway, it's like how big and heavy it is. So you have to know how heavy the item is, how the object is, how close they are to each other, and then the way that they pull each other towards each other has to be accounted for, and how that affects the orbit of the planet. It's pretty complicated stuff. It took a long time to refine it, and gradually the formulas were figured out to get the determination of perturbation very accurately. But it took many decades of astronomers working at this to get these calculations to show the effect of perturbation on the orbit. That's what perturbations are. So, to calculate the position of a planet, you have this kind of ideal perfect orbit, perfect ellipse, using Kepler's laws, and the planets gradually speeding up as they get close to the sun and gradually slowing down. But then you have the disturbances called the perturbations. Okay, now, perturbations cause the orbit of a planet to change. This orbit is called the osculating orbit. So here's the interesting thing. Let's go back to this image. How do astronomers calculate, when Mercury is here with its x's, you might think that they would calculate the gravitational pull of Mercury to Venus, and then they would pull Venus in a little bit and pull Mercury out a little bit. Well, that is correct. That's essentially what the calculations do. But they apply that disturbance, excuse me, that effect of gravitation, not directly to the position. I mean, intuitively, you might think, okay, Mercury's near Venus. Let's pull Venus a little closer to the sun. Let's pull Mercury out a little bit. But rather than apply it directly to the planet, they apply the effect to the orbital elements. Whoa, how clever is that? Let me say that again. Intuitively, you might think that a perturbation, as Mercury gets close to Venus, I'll just pull Venus in a little bit. I'll pull Mercury because they're getting close to each other, attracting each other. I'll know how big and heavy Mercury is and how heavy Venus is and how far apart they are. I'll calculate the gravitation. I'll pull them in towards each other. But instead of the formulas moving the planet directly, they measure its effect on the orbital elements. What's beautiful about this is by having the formula affect the orbital elements, then those new orbital elements are just put through the formula again, the simple Kepler laws of motion. You just change the orbital element and then recalculate. And amazingly, it works. It's just phenomenal. I mean, it's really phenomenal. You know, to think about it, that instead of doing the obvious thing of pulling Venus and Mercury close to each other, we'll figure out how it affects the orbital elements, and then we'll apply those elements, and then that is what happens. And this is why people say that the true node is not necessarily true, is because the true node is based on this disturbed path, the perturbed. Let's use the right word. It's the perturbed path. Now, to make this clearer, I've got a video that shows this. Let's look at this video. Let's, how did I end up with this thing so big? Let me shrink this down here. And okay, you can see that now. And here it is. I'm going to play this video. On the slide, it tells you where it is. It's called The Three-Body Lagrange Problem with Osculating Orbits by a fellow Volker Dorr, and there's the YouTube website. And this video does a beautiful job of showing how three planets, we have a yellow planet at the top, a blue planet in the lower left, I'll call it a purple planet in the lower right. And as these planets travel in their orbits, this is perhaps unrealistic because instead of them all going around the same sun, the same star, they're traveling around three separate stars that are close to each other. But that's okay. All we want to see is how the orbit of the planet, you see this orbits of these planets, as each of these three planets get close to each other, they're going to change the orbits of each other. I'm going to play it. Go. Okay, you see the yellow planet. He does this very beautifully. You see the dot, 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 dot. They're moving along. They're moving along. Now watch what happens. They're still far away from each other, right? They're still pretty far. When they start getting closer, the shape of the ellipse will change. Do you see it starting to change very slightly? Pretty soon it's going to become obvious. And I'll halt it after it starts really. Look at it change now. See that yellow? Let me stop it for a second. Look how big the yellow orbit is. It's now going off this black area. Same thing with the purple and red or whatever color that is. Let's continue and watch these orbits change. Getting bigger and bigger and bigger and bigger and bigger. Let me halt this. You see what's happening? The actual yellow is the actual path of the planet. But when this yellow planet is here, the orbit that's used to calculate its position is this big wide one. So we have what's called the osculating orbit. That the attraction, because this red planet is close to the yellow planet, the blue planet is close to the yellow planet. The red and blue planets are so close to the yellow planet, there's a gravitational attraction. That gravitational attraction is used to change the orbits of the planets. And at this moment, what's called the osculating orbit, this temporary orbit that the yellow planet is on, is now like this. The orbit has gotten distorted. By distorting the orbit, or more correctly with terminology, we say the perturbed orbit, or more correctly, this osculating orbit is used now to determine where the yellow planet is. I'm going to continue to play it. And now, as the planets get farther and farther away from each other, the ellipse is coming back smaller and smaller. So what perturbations do, and the way astronomers calculate it, is the perturbation affects the 6 orbital elements. And then the orbital elements determine the position of the planet. Why did they do it this way? Because it works. It works. It determines where the planets are. So let me show you this before we go on, just for fun. Here's another video. I think it's by the same guy. I think so. And anyway, let me play this. This is just pretty. Here's 4 planets. And you watch them get bigger and bigger. It's just kind of fun to watch. And then the orbits get smaller. It's just pretty to watch. Anyway, just for fun. You look at those orbits, and they spread out all over the place and they come back together. Now this is 4 planets becoming extremely close to each other. Nothing like this happens in our solar system. You don't get even 3 planets getting this close together, and the perturbations are not this large. But just for fun, this shows you how extreme perturbations could be. They don't happen in our solar system to this extent. What you'll see is more mild changes in the orbit. Okay, let's summarize what we've learned here. What we've learned is that, well, let me not go to this yet. Let me go back to, well, let me just stay on this image here for a moment. What we've learned is that you can apply Kepler's laws of motion and you get the planets fairly accurately. To get them more accurate, we have to take account of the gravitational pull of another planet when it gets close to a planet. And that gravitational pull will change the orbit, and that change is called the perturbation. So we have to take account of these perturbations. Astronomers did something not intuitively obvious. They have the perturbation, the effect of the gravity of the planet, change the orbit of the planet, and from that changed orbit, recalculate the position. That changed orbit is called the osculating orbit. The osculating orbit. So you might have thought that there's this clear, simple orbit in the sky, but it's not that simple. It's really just not that simple. There is not this clear, simple orbit in the sky, especially for the moon, because the moon has got huge perturbations. Why does the moon have huge perturbations? Because it's small relative to other things. So the bigger things, like Jupiter, even though it's so far away, is huge. And, Venus and, is affecting it when it gets close. So the effect of perturbations on the moon is fairly large. And the moon doesn't have a simple orbit. It has an orbit that each time the moon comes around, it's in a slightly different place and is affected by these perturbations from other planets. So, here's the bottom line. The bottom line is this. This osculating orbit, this orbit that changes because of the gravitational pull, it does accurately determine the real position of the planet. The big question is this: does it also determine the real position of the North Node? Some people are saying no. This osculating orbit, if you watch this thing, and it gets bigger and bigger and bigger and bigger. Let's go back. Let's go up here somewhere. We'll watch when it starts getting really big. This osculating orbit, as these orbits start getting bigger, we're watching them get bigger as the planets get closer. Okay, great. It helps us determine where the planet is. But if I stop this, does this big orbit here, this is the osculating orbit, used to determine where this yellow planet is, does the node of this mathematically defined abstract path? Does this abstract thing that I call it abstract because it's just used to help determine where the moon is, would this thing intersecting the ecliptic plane be a true node? It doesn't seem like it. And that's why astronomers are saying the true node isn't true, it's just osculating. Okay, so you can see why there's been doubt about whether the true node is really true or not. So let's pick up in the next video. Let's stop here, because what we've learned now is we've learned what the osculating orbit is. And the osculating orbit has in it a planet position, which is the actual position. It has a node, the so-called true node. More properly can be called the osculating node. So, number one, the true node in astrology is actually the node for the osculating orbit, so it can also be called the osculating node. Number two, reminder, the mean node in astrology is actually the node of the unperturbed orbit, so it can be called the unperturbed node. I'm going to end this video with this conclusion. From now on, at least until I get to the end, and then we can change the terminology, but for now, let's call the true node the osculating node. There's nothing wrong with doing that ever, because the true node is the osculating node. That's what it is. You now understand the astronomy behind planetary positions and behind the nodes. And you know now what the mean node is. The mean node is not an average node. That's a misnomer. It's the wrong term. It's the unperturbed node. So to repeat, the mean node is the node that's calculated using Kepler's laws of motion. You must calculate the unperturbed position first. Then you apply the perturbations. You must. That's how it's done. For every planet, you have its unperturbed position, and then you apply the perturbations to get the position more accurately. The mean node is simply the node before perturbations are applied. The mean node is the only mean position that I've ever seen used in astrology. Well, the mean sun is used in some forms of progressions, but the midheaven is moving at the same speed. Maybe there's one or two exceptions where people have tried to introduce a mean sun for certain predictive methods. But in general, almost always, if you're interpreting a birth chart or transits, you're looking at where the planets are, not where they might be if there were no perturbations. We don't care about that. We want to know where they are. It's like if you're going to get hit, if you're going to cross the street and get hit by a car, you wouldn't say, oh, gee, I wonder where the car is if it didn't slow down or something. You want to know where the car is. We want to know where the planets actually are. Using the unperturbed moon's node is an exception to the rule, and to me, it doesn't intuitively make any sense. Like, I want to know where the actual node is, not where the node would be if it didn't have perturbations. So what are my alternatives? Well, I can use the osculating node. That's the node for the osculating orbit. But again, the impression that astronomers have, astrologers who know astronomy, is that the osculating orbit is not a real orbit. It's an orbit that happens to calculate the position of the moon, does not mean it calculates the actual node. And what I'm going to show you I think I'll get to it in the next video, is that I've demonstrated through more analysis that the osculating orbit is actually the real position of the node. So at first it seems like, well, maybe it isn't, but it ends up that it is. And I'll show you that in the next video. Okay, my friends, thank you very much for listening. God bless. Namaste.